Okay, here we are for another quantum Stammtisch session. So for those of you who have been here already, you will know, this is the chance to have a bit of an informal conversation for the community at Quantum London. I know there are no good or bad questions. Every questions are good. And for those who are here for the first time, Quantum London is a community of people who has been exploring for the past two years and a half the business implications of quantum computing. So when is this arriving and what is it going to mean for our businesses? And trying to be on the not too technical side, so more on the use cases and the implications, business implications of the technology. So welcome for everyone who is new. And as we tend to start these Stammtisch sessions with a bit of an introduction from the people. If you are willing to, please feel free to introduce yourself in 1 minute or so, telling us a bit about your background and what brings you here. I will go around the room asking people to introduce themselves. Again, don't feel obliged, but it will be nice for the rest of the people who are part of the community to know who you are and what brings you here. And so yeah, we'll start maybe with myself, just very briefly. My name is Em. I work in insurance in the innovation space for a large insurance company. Spent a lot of my life in the UK and more recently moved back to Italy. For quantum, quantum for me is is a fascinating technology. I'm curious about things which are promising to change the world in the next future. That's something I'm really passionate about. That's actually what I do for a living, working in innovation. So I, together with Paolo, we started this group 2.5 years ago, trying to really understand a bit more about the technology and what does it mean. So yeah, welcome everyone, and yeah, I would be glad if you also be kind enough to introduce yourselves. I see first on my screen I have Mansoor Ansari. I see a really nice picture, a map of quantum physics. So I assume you work in the field, Mansoor. Is that correct? You want to give us maybe a short introduction about yourself? No worries. It's fine. And oh, here you are.
Oh yeah, hi. My name is Mansoor. I live in the United States. I'm American here in Oklahoma City, Oklahoma. Yeah. I come from about 35 years of classical computing, so I'm just learning this new stuff. And I also have a quantum computing group in Oklahoma City, so I'm trying to learn from you guys.
Fantastic, yeah. There is a lot of communities, burning nowadays. It's very interesting, both in terms of the technology evolving, but also the people getting curious about it. So yeah, we always welcome, collaboration and cross-pollination of ideas. So feel free to, if you find any synergies, feel free to get in touch.
Thank you.
Fine. Next one on screen, I have Manan. So nice to see you again.
Hello everyone. So quick introduction. I'm Manan and I'm based in India. Currently I'm working at Dell as a technician, but that's my day job. But the other quantum side is I work on developing a lot of things in quantum, basically hardware, software. So that is something that I'm looking forward to contribute there, and I enjoy these sessions a lot. I've been involved for the past couple of months now. So it's a great learning activity and where we can also meet other people who are involved.
Thank you. Thank you very much. And nice to see you again, Doug Walters.
Yeah, hi everyone. Yeah, I'm Doug Walters. I'm an enterprise and solution architect. 43 years in IT, so I'm getting pretty old. And one of my things I do is I sort of track emerging technologies and try and understand their applications. I'm currently going through quite a lot of research on quantum, identifying not only where people think it may be useful, but also understanding how the technology restricts where it can be used. And there are a lot of restrictions where no matter whether you think it would fit the quantum would fit the requirement, the use case. It just won't hack it in terms of the way it operates. So I'm trying to put that a sort of a short paper together on that as well to understand better.
Okay, that's fascinating perspective. So I'm curious to know more. Maybe we can, when we kick off later the actual session, you can give, if you're happy, you can give us a bit more around that.
Yeah. Okay.
So next one I have Gunther Dirks. Welcome to the community. Feel free to introduce yourself very briefly if you want. Okay, no worries. Next one I have Amira.
Hi there.
Hello, hi.
Hi. So I was working for 10 years in IT, and then I started a master's in information security. And then in my dissertation there, I did quantum computing and what's the impact on information security. And I got really interested. I always had quantum in the back of my mind. So this just got me deeper into the subject. And now I'm looking more into it, and just, I live in London. I saw Quantum London, so I joined. This is my second time in the meetup. And I'm trying to find my way through it professionally, hopefully as well. So yeah, that's
fantastic. I know Paolo is very keen to start getting back to mixed events with physical presence. So we'll shortly let you know when that happens in the coming future.
Yeah, especially July.
Thank you. Thank you very much, and welcome. Gunther, I don't know if you want, I saw you coming back on camera for a sec. I don't know if you want to say a couple of words about yourself. Hi, hello. You might be on mute, but I see your camera. You're still on mute, but I see you're talking. So looks like we have some difficulties hearing you. I will move to Karnajit and then come back to you, Gunther, whilst the audio is sorted. Hello, hi. Hi, Karnajit.
Hi. So my name is Karnajit. I'm currently in Germany, and I'm a researching scientist in BSF. So I mostly work with quantum chemistry a lot, and that gives me so I'm always interested in quantum computing. So I found your group, and then thought why not joining it and listen to you what is getting discussed here.
Fantastic, and
so
thank you and welcome. Is that your first time here?
Yep. Yeah.
Okay, good. You need to explain what BSF is because that's a new term for me.
Oh, BSF is a chemical company. It's the largest chemical provider.
Oh, sorry. Oh, yes. I thought it was a BSF.
No.
There is an A in the middle. Okay, apologies.
Yeah, it's yeah. I hope now you got it. So anyway.
Okay. Thank you and welcome. Kate, I have you next on screen. Welcome.
Hi, I'm Kate. I'm in the United States in the Philadelphia area. I'm a design researcher for IBM Quantum. And right now I'm working on trying to understand who is interested in quantum and who's using it. So all of you. So I'm really working in the user experience space, if you're more familiar with that term as opposed to design research. But also second meeting. So happy to be here. Thanks for having me.
Thank you and welcome. Nice to see you again. Next one I have Rory. Welcome, Rory.
Hi.
See you again.
Hi. Yep. I think I've been at 3 or 4 of these now. I live in the UK, but I work for a large German financial company where I'm heading up research into quantum and how we can apply it in financial markets. Similar to what Doug was saying, I'm currently looking at a sort of sales pipeline qualification process for quantum use cases. So what sort of questions do you ask to qualify something in and something out? How do you find useful opportunities to apply quantum in the enterprise. So trying to work on that for practical reasons, but also because I haven't seen anything out there that does that.
Yeah, once again, I think that's a fascinating topic. I would be really keen to maybe explore it with the rest of the people in this course today. Let's maybe kick off with that. Thank you and welcome, and nice to see you again. We got a couple of people still to go through. Ivan, hello. Nice to see you. If you want to share a few words about yourself, otherwise, no worries. We will move on to Mike. Mike H.
Yes, hi. I'm a software engineer in New York, financial industry. And I start getting into quantum like this year. Yeah, I'm just trying to learn. So,
Okay, good.
Thank you.
You're most welcome, and welcome to the group. Jim Walker, I think I skipped you previously. Welcome to the group, Jim. Nice to see you again.
yeah, it's good to be here.
Fantastic. And I got Gunther.
Yes,
hey.
Maybe you can hear me now. Thank you.
I can, yes.
I'm from Germany, and I'm very much interested in quantum computing. We think about a project with deep learning with imperfect information and put it on a quantum computer of Microsoft. I think it will be interesting to learn from you all. Thank you.
Okay, welcome to the group. And finally, we'll close up with Paolo.
Hi, thanks. So, yes, delighted to be here. As Em said at the start, he and I kicked all this off a few years back. I also work in the insurance industry, but sort of beyond that, I just like thinking about where new technologies should be making impact in the real world and in business. So yeah, it's fascinating to reflect on when we started having these discussions a year and a half ago when we first went online. There were relatively few people saying, oh, I'm just curious about this topic, but who were also able to be doing things. And I'm just listening to some of your introductions now, the number of people who've said, oh, I'm starting to do things in quantum is fantastic. So really looking forward to these conversations. We've always found that they've allowed people to ask all sorts of questions. And for those of you who are actually doing things in the context of your work, to share little bits of that to help us understand the direction all of this is going. So look forward to the next 30 or 40 minutes of conversation with you all.
Thank you, Paolo. I will probably kick off with the topic that Doug brought on the table. Do you want maybe to elaborate a bit more on the topic, and maybe we can have a bit of a conversation around that?
It's very early doors, so I'm not going to pretend to be an expert, right? And I'm just sort of one of the things that struck me is that a number of people have talked about, and Jim Walker may be able to comment on this, is that there's one of the limitations of quantum is its ability to read data to actually consume data. That it's not a sort of, if you like, a mass volume technology where you can actually sort of consume, sort of gigabytes of data and then use that to create learnings. So that then seems to sort of limit what I originally thought, which I thought, well, this is a way of increasing the speed of, and this is very naive of me, increasing the capacity and speed of machine learning. And I don't think, from what I've seen so far, that is the case. But I'm one of the reasons that I'm quite happy to say that is that hopefully somebody can put me right.
So, well, I don't have an answer to that, but I'm wondering whether is that something is a limitation of the number of qubits we have today, or is it always going to be the case? We touched on previously on preparing data to be represented on quantum computers for machine learning, but that seemed like a very complex topic and a discipline in itself. So, but I'm trying to bring it to more simplified level. I don't know if anyone has the answer. So what Doug is his argument, is that because of the number of qubits we have today, or will it ever be the case that will be only, we will never be able to ingest a number of...
It's a range of throughput to be able to read data, which is, according to my research so far, so I'm limiting in that, no personal experience of it, seems to suggest is actually not as advanced as classical computing.
I mean, I think like an analogy of, when internal combustion engine cars came out, they were slow and they broke down, and certainly in the UK, you had to have a man walking in front of you with a red flag to be able to drive them. So in terms of transport, you would look at it and say, this is worse than a horse, because the whole infrastructure was designed for horse transport. Yeah, so we're kind of thinking in terminology of classical computing, where we represent things in bits and we load up large sets of data and we create imperative algorithms to process things, versus thinking in quantum terminology, where we might not load a vast data set into a quantum algorithm to get the types of results that we want to, which is what we do classically. If you look at like some of the most famous quantum algorithms like Grover search, it doesn't work the same way that a classical algorithm works, because it's based on quantum physics rather than classical physics. And unless you've done a computing science degree and you've got a really big, strong background in it, most people don't know how classical computers work either. They're at a sufficient level of abstraction that, we just use them. I think...
Sorry, go on. Sorry.
I was going to say, I think that's the problem at the moment. Our term of reference is classical computing, so we always think in those terms. That's the difficulty, I would say.
And there's two issues I think that need to be addressed as a result of that. One is, do we think that there is a limitation in the architecture or the very concept of quantum, which prevents us, generally speaking, improving the throughput? That's the first question. And therefore, that we're constantly going to limit the applicability of the technology. And the second thing is, it's certainly for quite a period of time going to limit what people are going to develop and invest in, and therefore restrict the traction that quantum, sort of will get in the industry. If you see what I mean? It may well get there in the end, and that's fine. That's what's one issue. And the other issue is, to get accepted, you've got to have a number of use cases that it can satisfy, that people will say, okay, that's the go-to technology for that type of use case. And I'm talking about a very abstract level here. And if there isn't sufficient of those types of situation, then you're not likely to get the traction in the industry, the momentum to actually, sort of onward develop. So I think there's two issues there, and I'm nowhere near sort of getting a solution at the moment. I'm just posing questions. I don't know if anybody else has any thoughts.
Yeah, I think there's a bit of a hype. We're in that sort of hype cycle at the moment, and one of the tricky things is to manage the dismissal of quantum, and at the same time I can see that there are companies out there that are raising huge amounts of funding, and it could be another .com bubble for those that are old enough to remember that. And it's how you manage in between those two and say this is going to be productive at some point, and there's an appropriate amount of funding. So we're kind of looking for the quantum Goldilocks zone, you know, not too much and not too little.
I think you said more eloquently. What I was trying to say is that, you know, so we've got to try and find the things which will encourage others to take up quantum as a valid proposition, as a valuable proposition. Yeah.
Yep. And there's definitely use cases out there that are more popular than others. So, like trying to find a use case, if you don't need, if there's not a single perfect answer to be found, if you're looking to optimize something, you don't need to find necessarily the most optimal answer with quantum. You just need to find a more optimal answer than a classic algorithm gives. So, for example, in finance, there's sort of collateral optimization. How do I place my collateral in the most efficient way? If I can find something that's a few basis points better than the best classical algorithm, it doesn't matter if it's the best possible solution. I don't need it to be a perfect answer. I just need to find one better than what everybody else is doing, and that makes me money, which is essentially how we'll get the adoption. So that's the type of thing which I think lends itself better to quantum. You know, if we've still got this noisy intermediate state where we're getting errors in our qubits, it's fine, because if I can still show that the answer that I get 95% of the time is better than a classical one, then, you know, that's great. Whereas if it's building bridges or aircrafts, you can't really be 95% there. You won't be allowed to build that building or build that aircraft. So there's some things that work and some that don't. And I don't have the guidance, you know, the heuristics yet to say how you find them, you know, in the insurance industry or in chemical engineering or whatever. But I think there's a lot of interesting things to work out there. And that'll be part of the journey.
Yeah, and so bottom line for me at the moment is, yeah, I thought that this was an interesting way to look to address the problem. Is from the technology perspective, what the technology limitations are at the moment, and what the roadmap for the technology looks like, and sort of then actually see what the business applications could be within that. The constraints of that. It's a slightly different take on it.
Yeah, I think it's a fascinating perspective actually, because, you know, everyone is going through, oh, quantum is going to change the world. No one is being explicit on what quantum cannot do. I think they might come up with a really nice paper, Doug. So I'm really looking forward to that.
Yeah, well, I'd be quite happy to. So once I've finished it, I'll be quite happy to share it.
Absolutely. Jim, I think you came off on camera for a second. I don't know if you wanted to say something.
Yeah. I you know, as you know, I'm a quantum engineer, so I'm literally at kind of the qubit level at Honeywell, and also you guys are, you know, Quantum London. You're familiar that we're merging with CQC as well. So soon there'll be a lot of additional information and cohesion between us and capability and so on. But last Friday we put out a paper on quantum error correction. To that point was raised in that discussion, and we're able to do multiple types of error correction, and that's what was discussed. There's other things going on, of course, but the point is that we're achieving error correction already that is significant in terms of it allows us to correct as we go in real time, basically. But the bigger thing that I would say is that we are at the beginning, but the amount of capability that the qubits provide compared to a digital approach is significant in terms of depending on the the area, and in terms of optimization problems that are CS centric and classified more from a computer science perspective. Sure, we're going to be doing great there, but honestly, it's going to be the AI and the molecule modeling and the life science areas that are actually naturally kind of quantum already, that those actually are just getting started. So it's kind of beyond our imagination, actually, most of us, that in terms of what's really happening here. The thing that's being presented to us in terms of capability, we actually, most of us can't relate to at the moment. It's not, it will take years for us to actually relate to what we're exposing and just beginning to expose. We're very, very early in this. It's extremely exciting. I work in an environment where literally every day there's a new thing in terms of a new breakthrough, a new innovation, basically, and only a portion are getting released publicly. But that I don't have any doubt in it because I'm in that environment. But if you don't have connection with a quantum computer, literally, and I'm like watching one run right now, basically, and I'm on the operations team for a quantum computer. So the point is that I'm literally seeing the things happen, but a lot of us aren't, most of us don't have that kind of connection. But I'm just here, in the trenches to say that it's really fantastic in terms of, and it's beyond our imagination as far as the capability. And you don't need millions of qubits. You can get by with a very small number of qubits because of their power. So, and it's not a 1-to-1 or a 1 to 1,000, 1 to 1,000,000 kind of relationship. It's something completely different that is not something, we're going to have to come up with a new lexicon to really describe it, and our brains won't be able to understand it, although they already know it under the covers. Our systems internally actually work in this manner, but we have to kind of relearn how to even describe these areas. So anyway, I want to give a little input from the trenches, so to speak, that relative to what was discussed, basically. So.
Thank you very much, Jim. But may I ask my personal question, because I'm still trying to get my head around it. So I understand, it's a new paradigm. We need to shift the way we think about it. But when we say, quantum computing is going to make a difference for for machine learning, for example, and then on one hand we think, oh, machine learning needs a lot of data to work. How do we then, squeeze in those data into the quantum computer? Or is it a silly question because, there will be completely different ways of thinking. So this is not really a question we should be asking.
Well, the way that obviously there's a whole bunch of things. I'm focused on certain areas. So there's going to be much better people to speak directly to that. I'll just say that if you currently we're representing that data digitally and we're injecting into a quantum computer, but if you actually had that data in a quantum form, for example, what would that be like? Where it already was quantum, and as you know, once you have a qubit in superposition, it has the ability to hold infinite states, basically. So imagine that, but you can imagine that. In other words, the point is that that's just I don't know if that's correct or not, but the point is that I see elements of that being correct in terms of that. That's the way I think about things now. But honestly, to get to that level of thinking, I don't know how to help other people to do that, other than to be on these calls or something. But the point is that it's an entirely different way of thinking, and I'm surrounded by PhDs and scientists that help me understand these things. But I eventually developed my own intuition as well through osmosis, basically, and the work that we do. But the point is that I believe that AI, for example, initially they're trying to force it into a translation between digital and quantum, but I'm saying there's an entirely different door available to our area that's not actually it's being exposed, but we're at the very beginning of that. So it's very exciting.
So are you saying that there needs to be, if you like, a bit of pre-post processing data wrangling before it gets into into quantum, or have I completely missed the point?
Well, I'm just saying that that's where we are today, where we're forming different representations of data to interact with a quantum states and capabilities, basically. And I'm just suggesting that ultimately these things, that area is going to keep getting closer as far as the representations of data will change, I believe, to make use of the huge capability that we're now exposing. So I'm just suggesting that that's very likely to happen, and that the techniques today are driven by just what we can do today, but they limit us. But honestly, we're getting results that are already starting to go beyond what the capabilities without quantum are. So even with a few, not with that many qubits, basically. So the point is that we're already doing it. We're already achieving things, but it's going to get a much better as people will naturally want to connect the two more directly as time goes on. And when that occurs, it's going to be fantastic, because at a quantum level, things operate in ways and capabilities that are literally beyond our imagination. We can't even imagine what these things are like. And that's why it's so difficult to discuss, because it's literally beyond our imagination. We don't have any context for things, but we're starting to develop that. I've developed it myself, and I know others have.
How long have you been? Sorry to interrupt. How long have you been working in this field with?
Just 3 years, and that's from scratch. I'm straight computer science, like cloud computing type engineer to quantum engineer. So the point is that I didn't know anything about quantum really before this.
Okay. And what was up? And have you seen an exponential increase in our capabilities with quantum, or has it been a slow burn during those 3 years?
I think it's mainly just achieving the things that we believe are possible, and we made it happen, kind of thing. And in terms of our team's been very successful, and continues to be. In other words, we just keep hitting these milestones effectively ahead of schedule almost, which is really unique. I've never seen it like that before, but our organization's been able to do that. And it's just a progression of, but the raw capabilities actually existed almost from day one when we released our first commercial product, in terms of, we have the capability of like very high fidelity qubits and the mid-circuit measurement. We can make measurements in the middle of a circuit, which nobody else can do. Those two things alone are very significant compared to other quantum computers. And because we're dealing with ions instead of locked in circuitry, the amount of effort you have to do to unwind and so on a circuit-based quantum qubit compared to an ion-based is significant. In other words, just to connect any qubit in a circuit is very, very difficult when it's stuck there, basically. And we move them around. And so our technology they went with, and we're just making it happen, basically. In other words, I'm not seeing, I mean, all the things are happening, but the architecture hasn't changed in terms of, we're adding more qubits and things like that, but it's like, we have a neat path in terms of, where that's going. And what we're finding is that you don't need that many qubits to actually get fantastic things done. It's the quality and the capability to easily connect to qubits that appears to be more important at the moment, basically.
Okay.
What's about the quality of your results with the low qubits? Because we work with Microsoft Quantum Computer, and we use, at first we started with less qubits, then we worked with 30 qubits, and the result was not so good. We put the data on the high performance computing of Watson to compare it, and we had 6% better performance in the high performance computer of Watson compared to the quantum computer.
Yeah, I'd have to know, like when you said Microsoft, I'm not familiar with Microsoft's computer, but I don't know what computer that was. But
we have a slot there. We have different slots. We have from 8 qubits until 40. You can get free access, and we used it. And then when we had the results, we put it. We put the whole data stuff on the high performance computer of Watson, and we had a very much better result, because I think the noise is a problem at the qubits. If you have 2 less qubits, you have a lot more noise than if you have more qubits on Microsoft. I think they use a topological qubits, and these are more exact.
So what you just said is curious to me, because a topological quantum computer doesn't exist yet. So you're still not answering my question in terms of what you actually ran on, but it's not that important. It's unlikely that you ran on a Honeywell computer, because what you're describing is exactly what people experience when you have qubits which are not high fidelity and don't maintain their fidelity. And that's what we've achieved. We've achieved it since the beginning, basically. So the thing that's happened with us is that companies that have run like an experiment like you're describing, exactly like we've described, the signal to noise ratio is it's very difficult to pick out this signal out of the noise in a quantum computer that doesn't provide good fidelity. And so we've achieved that, so that people that have had that experience have come and done the same programs exactly on our systems, and they're like, oh wow, we can see the signal. The signal's like right there. It's like it meets their expectations immediately. So anyway, I'm just saying that we're in that phase. Not all quantum computers are the same right now. So we're at a stage, it's early, so that all those details become important, basically. So once you see it, though, these customers don't go back. In other words, when they really want the real results, they use our computers, and that's just where we're at. It's not, I'm not boasting or anything. It just happens to be the situation that the details matter right now. And,
thank you very much. It's very interesting for me.
I would like to go back to Doug's question and open up to the rest of the group. Are we seeing an acceleration? What is the feeling from the people around this table? Before I give you my answer, I would like to see if anyone has any comments on this point. Are we seeing any accelerations?
In like the industry, in quantum computing industry?
Yeah, in the industry as a whole, yeah.
Yeah, certainly. I believe so, but it was stated already that just as it was described, that there's a lot, it's early stages, so that you see that in the form of perception versus reality. And as you guys know, since most of you are primarily maybe in the business sectors, perception can be very different than reality. And I think that there's a lot of opportunity just with perception to make a lot of money, possibly, but it doesn't mean that it doesn't mean that the reality of the science and the capability really is what people are saying. So I'm very because I happen to be in where I'm at. I can have a better, I can distinguish reality versus perception a lot easier than a lot of people, perhaps.
So yeah, I think that's basically the answer I would have given. I mean, there's certainly an acceleration in the number of noise, and the amount of times we hear about quantum computing, and it's also true that not something is a bit of PR, let's call it this way, more than it is substance. But if you think behind all the noise, right, there should still be some substance, right? So I think it's great to see that people are pushing the boundaries. I think it's all good that we're seeing more and more stuff coming out every day. And also I think in terms of investments, yes, there is a risk of the hype and the bubble, but also when you create this virtuous cycle of of a bit of noise, also then when invest comes in, and then that boosters the innovation and new things coming out. So I think it's not too much of a bad thing having a bit of noise there. Manan, I think you have unmuted yourself. Maybe you want to comment on this point?
Yeah, just a second.
Please.
Can you hear me?
Yep.
So it's like I just have one question over here, that why is ion trap qubits better than the superconducting ones? You said that they can move around, but what makes them unique, and what better things are we achieving with them? So I have this for Jim, like.
Well, you can look at them yourself, but basically, currently the ion traps produce higher fidelity qubits, and then because their ability to move, we actually have there's different types of architectures for ion traps. There's some that actually don't move the qubits around, like IonQ, and they do, everything is kind of in the same well, effectively, but when you do move the qubits around, it allows you to do the 2-qubit entanglement, basically, much more effectively on the real atom or the real qubit, at the same time, basically in the same place, essentially. So that appears to be an advantage. But there's other advantages in terms of the ability to measure. You have to understand that in a superconducting qubit, it's very difficult to initialize a superconducting qubit. It actually takes a lot of time. It's a hard thing to do, but it's also hard to measure a superconducting qubit. And those are easy things for us to do in an ion trap. It's just using lasers and optics and so on. So all of the operations have different, each operation, which is only about a dozen operations really in a quantum computer, they all have a certain cost and complexity. And the advantage is that we can do all those things very well in an ion trap. The disadvantage is ours are slower than a circuit base, but it doesn't matter if the fidelity is so much better. Ultimately, that's what we're seeing, is that's what we banked on, and it's basically, becoming true. But the ability to measure a qubit and then reset it so that it can be reused, that's very powerful. So that superconducting qubits today don't have that ability. They're working on it or whatever, but they can't reset a qubit right now. And so they're forced to, they'll run out of qubits very quickly in a program, where you can imagine that some of our qubits can be temporary. They can be used multiple, hundreds of times perhaps in a program, whereas if you can't do, that's what you're used to in a normal program, basically being able to reuse a variable. But many architectures don't support that. So I'm just pointing out a few items there.
Yeah, thanks a lot, because I was just considering to make an entry, as you know that we're not in the game right now, so we have to know where we have to start superconducting qubits or ion traps. So it was a very valuable insight that you gave, so I would surely consider that as well. And I think we have Kate also, so I think she's at IBM, so she would know better with the superconductor side.
I would love to be able to comment on all the technical details, but I'm way far back from that. I'm over in user experience, so I'm doing evaluations with the business team, but not so much on any technical understanding.
But in business side, like suppose, what do you see in the consultancy side? So suppose if there's something that needs to be done, other players, other companies, if evaluation needs to be done, so what can be done down those lines?
I'm not sure. I don't know if I can answer that. So like I join all these meetings at work to observe, and the group that I'm working with is just talking a little bit over my head. So I think this is also a conversation that's a bit over my head, but I appreciate you trying to include me in the conversation. It's very kind.
Thank you, Kate. But I do have a question for you. I mean, are we seeing any efforts into trying to create abstraction layers so we do simplify the mechanics that sits at the ground level? So from your perspective, what kind of efforts are you seeing in terms of, because you work in user experience, that means people using it, right? So I suppose there must be attempts and efforts in trying to build abstraction layers that make it easier for people to use quantum computers. I don't know, is that something you are willing to comment on?
Yeah, I can't say too much, but my experience with the Qiskit team, that the researchers who work with, the users of Qiskit are really in touch with trying to approach all levels of understanding. So I would say yes in terms of Qiskit, but not necessarily able to comment on the work that I'm doing.
Mm-hmm. Okay. So if I may ask,
there's an IBM roadmap.
Mm-hmm. Yeah, please, Rory, go ahead.
Sorry,
go ahead.
There's an IBM roadmap. There's an IBM roadmap that I'm familiar with, but I mean, all the vendors have got roadmaps like these that sort of shows the evolution across their Hummingbird, Falcon, the different chips with the different number of qubits they've got. But then vertically, the roadmap shows the increasing levels of abstraction where, people, you can go and look at a Hadamard gate and it tells you the microwave pulses that they're firing on the IBM machine to actually implement that gate. And then it moves it up a layer to circuit design. And the idea is eventually you move it up to model design. And that's kind of what I meant when I said a lot of people aren't familiar with how classical architectures work anyway. So, when you're writing something in what you think is a low level
C++ or whatever. It's actually, you know, a million miles away for the actual electronics engineering of the chip. So, you know, we've got to remember where we are in classical computing. We're way back, you know, Charles Babbage or Alan Turing sort of era in quantum. And it will need that level of abstraction. And when we get to that, I've no doubt there'll be competition between photonics and superconducting and ion trap, but it'll become an abstraction potentially. And we need to raise the level of abstraction so that everyday people will be able to use it in the way that classical computing has moved, so that the masses can participate.
Yeah, that's a good point. It's a good point.
I love to think we are at the before the transistors at the valves state, not as back as a Babbage, but we can argue.
Yeah. What's 100 years between friends?
Okay.
Oh, wish we were here in 100 years and see how it spans out. But I also read in the IBM roadmap that they have something about logical qubits that will be possible. And would that mean a big change in how how processes are going to be? Because that would mean less errors and things like that. And I think it was 10 logical qubits for every 1,000 physical qubits. So yeah, that's in the future, but I was wondering what's the repercussion of having logical qubits versus just physical qubits? One of my questions in my head.
Well, it's that whole thing about fully error corrected, and that's why people are looking for quantum algorithms like we talked at the start about. Do you need an absolute precise answer or a 95% and 90% answer being good enough? If you need to wait until you've got whatever it is for, you know, breaking in RSA encryption, you need like 300 error-corrected qubits. So that's potentially what, 30,000 physical qubits. So that's potentially a long time away. But is there useful work that you can do now with, you know, 50 or 100 still noisy qubits and still get value out of that? That's the sweet spot, I think, at the moment, is to find use cases where you can apply something and make traction. We did a use case, and one of the things that we did at the end of that was say, how much would we need to actually, you know, make this useful in a real world scenario, and how far away is that? Because you can prove that something will work with a quantum computer, but if it's still 30 years before that will be available, you're probably not going to get funding or, you know, get investment to go and explore that. 30 years is too far on a horizon for most people. If you can demonstrate that you could have it in production in 3 years, well, people can do ROI calculations on that.
Rory, and I think that point, as well as what you said at the start, and in some ways summarize sort of exactly what we need to do next, which is to, as we start to say, what are the problem sets, what should we be trying to solve, understanding those things where marginal improvements over the current way of working, which can be done with machines that aren't perfect, is clearly the way to go. So, you know, a slight optimization over what we have today is great. Trying to design something where you need it to work 100% is, you know, not going to happen immediately. So thank you for sharing those thoughts with us. I think as we wrap up, it's always interesting. You know, we try and run the Quantum London group in a way of saying, you know, what are the business impacts? And we tend to always get into these discussions, and I find them fascinating. You know, I used to code in hexadecimal, which wasn't quite at the layer of programming machine chips, but pretty much there. It's the fact that we keep returning to these fundamental questions around the physics and how they work means, I think, that we're not yet ready to engage with executives. But as a group, hopefully we'll continue to be working out what's the language that works. And You know, the reason people like you, Kate, are invaluable in this group is you can say, hey guys, you know, I just understood absolutely nothing that was said for the last 20 minutes. So if you went and took that to a CFO or a CRO in a company, that would be a big fail. So really appreciate it when people say that some of this isn't making sense. I'm aware that I'm probably hard to hear because I'm stuck in a very busy station. So I just wanted one final point, if I might, which is for those of you based in London, I would love to get us physically together when people start to feel comfortable. I'm proposing a small pilot exercise on the 2nd of August. So we'll put that in the meetup. Anyone who wants to do that, it would be great. Let's see how that plays out. But we're definitely going to continue these online sessions. The next couple are already on the meetup and on LinkedIn. So thank you for joining us. Thanks for a great conversation. And before I close, Kate, I saw you came off mute. Did you just want to add a final point?
Oh, no, I was just agreeing with you that it's sometimes hard to follow, but I appreciate the open forum. That's all.
That's great. Thanks, Kate. And I really love the nature of the discussion we've had today, because it's forced us down a road of saying, look, there's no point laying out all the possible business cases and getting excited about them. Let's think about the ones that may actually be solved in the next year or two, because those are the ones the investors need to be getting behind, because they're the ones that we can then satisfy those investors that they're getting a return on their investment, and then that'll encourage them to invest in the stuff that's going to take 5 or 10 years to deliver on.
Yeah, that was my original thinking.
Yeah, fantastic. Well, thank you for all your thoughts. Apologies for the background noise where I am. Look forward to the next one of these discussions in a month's time. And just in case you were wondering, we are going to have some webinars and panels again. It's just Anna and I have been so busy we haven't managed to arrange them. If any of you have good speakers or anyone you think would be interested in doing a webinar, do let us know, because the most difficult bit is finding the right speakers. So if you can give us any suggestions, then actually setting up the logistics we can do quite effectively. So thank you. Good afternoon and good evening.
Thank you.
Bye.
Cheers, thanks, bye.